This is going to be our third video on solutions. In the last video, we started to talk about colligative properties. We talked about vapor pressure lowering, how when you dissolve up a solute in a solvent, you lower the vapor pressure of the solvent. The next colligative properties that we're going to talk about are freezing point depression and boiling point elevation. When you dissolve up a solute in a solvent, you depress the freezing point. The solution freezes at a lower temperature than does pure solvent. You also elevate the boiling point. The solution boils at a higher temperature than does pure solvent. So we can calculate these with these two equations. Delta T is Kfm, or delta Tf for freezing point, and delta Tb is Kbm, is B for boiling. Where delta T is the change in the freezing or boiling point. It's not the freezing or boiling point of the solution, it's the change in the freezing point or boiling point. So it's the amount by which the freezing point is depressed or the boiling point is elevated. So, and Kf and Kb are the molal freezing point depression constant and molal boiling point elevation constant. And of course, M is the molality of the solution. Okay? So for water, these constants are 1.86 degrees Celsius per molal for the freezing point depression and 0.51 degrees Celsius per molal for the boiling point. So one more time, this means the change. This means the change in the freezing and boiling point. So for example, let's say that you had a 1 molal solution of sucrose, okay, or some non-dissociating solute dissolved up in water, right? So water normally freezes at 0 Celsius. So your solution would be depressed by 1.86 degrees Celsius. So it would freeze by at minus 1.86, right? Same thing for your boiling point. Let's say you had a 1 molal solution. Okay, water normally boils at 100, so your 1 molal solution would boil at 100.51. All right, and these constants are unique for every solvent. Okay, so these are only valid for water. They are using cyclohexane, for example. They're different. If you have using acetone, they're different. Let's work an example. Okay, so let's say if you read a can of cola and says that it has 39 grams of sugar present. Let's assume that's glucose. Dissolved up in 355 grams of water, what would be the boiling and freezing points of the solution? Okay, so what we've got to do here is calculate the molality of the solution. So we have to take that first of all, we got to take that 39 grams of glucose and convert it into number of moles. So 39 grams, if you look up glucose is C6H12O6. That's 72. 6 times 12 plus 96 works out to be 180 grams per mole. Okay? So remember how you convert grams to moles, you divide by the molar mass. So you have 39 grams divided by 180 grams per mole comes out to be 0.22 moles. Okay, 39, so we'll come back to that. So 355 grams, remember that molality is moles of solute per kilogram of solvent, so we have to convert that into kilograms. Divide it by 1,000. So 0.22 moles divided by 0.355 kilograms is a 0.62 molal solution. Okay, so how do we calculate the change in the boiling and freezing points, right? So we'll do the boiling point first. So that's kBm, so 0.51 degrees Celsius per molal times 0.62 molal is change in temperature of 0.31, right? So water normally boils at 100. This is the amount by which the boiling point is elevated, right? So it's going to boil at 100.31. Okay, we'll look at our freezing point, the same thing, except it's 1.86. Freezing point depression constant is different. It's 1.86 times 0.62 is 1.15 degrees Celsius, right? So what's our freezing point? 1.15 degrees below the normal freezing point, which is 0. So 0 minus 1.15 is minus 1.15 degrees Celsius. So what you're seeing here is that the boiling point, the boiling and freezing points really didn't change that much. 39 grams sounds like a lot. In fact, it is a lot. That would fill up, we used glucose in the previous example. 39 grams is a lot, and that would fill up at least a 100 ml beaker, at least halfway, but the problem is it's so heavy. And one more time, your colligative properties have nothing to do with the mass. They have to do with the moles, the number of particles in solution. So if we had a lighter weight, if we had a lesser substance, let's say with a lower molecular weight, and that 39 grams were a larger number of moles, then these changes would be bigger. All right. So you can also use this to calculate molar mass. All right. So let's say we make a solution by dissolving 3.46 grams of benzene, or I'm sorry, 3.46 grams of an unknown compound in 85 grams of benzene, and it freezes at 4.13 Celsius. Okay, what is the molecular mass of the compound? What's our strategy going to be here? What are we after? We're after molecular mass. Okay, what are the units on molecular mass? That's going to be grams per mole, right? So you already know how many grams we're putting in. Okay, we know how many grams we're putting in. We need to know the number of moles, and we're going to get that from the freezing point depression data. Because if we know the change at freezing point, we can calculate the molality of the solution. And from the molality of the solution, we can calculate the moles of solid. Okay, so one thing you need to know is the normal freezing point of benzene. You'd have to look that up, or it would be given to you. It's 5.45 degrees Celsius. So the first thing we're going to do is calculate our change, right? You can see where the freezing point was depressed. Benzene normally freezes at 4.13 Celsius, or I'm sorry, normally freezes at 5.45. Here it froze at 4.13. So by how much did we depress the freezing point? 1.32 degrees Celsius. Okay, now there's something else that you need to know, and that is the freezing point depression constant for benzene. Okay, and that is 5.07 degrees Celsius per molal. All right, so we're going to take delta T, which is our equation. Delta T is equal to KFM, and rearrange it to solve it for M. Okay, what we want to calculate is the molality of the solution. Right, so M is delta T over Kf. Okay, so 1.32 degrees Celsius divided by 5.07 degrees Celsius per molal finds out that the molality of our solution is 0.260 moles per kilogram. Okay, well, how does this help us? Remember what we're after. We're after the number of moles of solid, so we can calculate the molar mass. Well, if we know the concentration of the solution, we just figured out the concentration of the solution, and we multiply that by the mass, then we'll have the number of moles. right? Moles per kilograms times kilograms will give us moles. So we take 0.260 moles per kilogram. Now to convert 85 grams into kilograms, divide by 1,000, that's 0.085. Tells us that we have 0.022 moles. So what's the molar mass of our substance? 3.46 grams divided by 0.022 moles is 1.57 grams per mole. Okay, so you could use any of the colligative properties to figure out a molecular mass like this. For example, like the vapor pressure lowering that we talked about in the previous video. You could do the same type of calculation. If you measure the amount by which the vapor pressure is lowered, and then you can determine the concentration of the solution, molality of the solution, and then use that to get out the number of moles. Okay, so third colligative property is dialysis and osmosis. All right, so dialysis is the passage of small molecules and ions, but not colloids, which are bigger, through a semi-permeable membrane. Okay, and osmosis is the passage of solvent, but not solutes, through the membrane. So when you have a solution and pure solvent separated by a semi-permeable membrane, the solvent molecules migrate from pure solvent side into the solution side. All right, so we have something like this. I have a U-tube set up here with a semi-permeable membrane. Let's say we have pure solvent on this side and solution on this side. Then there's going to be a tendency here for the solvent to migrate from the pure solvent to the solution side. Okay, in other words, this will go down, and this will go up. In other words, there's a tendency for things to become more diluted like this. All right, so that's basically osmosis. Okay, so osmotic pressure is the back pressure necessary to prevent this from happening. All right, so let's go back to this. So we can stop this from happening if we apply a pressure to this side. Okay, and that's what osmotic pressure would be, the pressure necessary to prevent this from happening. Now, if we apply greater than osmotic pressure, then that's reverse osmosis. So we use greater than osmotic pressure to force the pure solvent through the membrane. Okay, so osmotic pressure is just the pressure that's enough to keep this from happening. And if we apply a greater than osmotic pressure, we do reverse osmosis, and we force it to go the other way. Would force it to go the other way. In other words, this would go down and this would go up, and we would be making more pure solvent. Okay, and that's how they purify water, by reverse osmosis, is forcing it through a semi-permeable membrane under pressure. The solvent can pass through this membrane, but the dissolved solutes cannot. Okay, so our equation for osmotic pressure is pi, it's uppercase pi, is equal to mRT, where pi is the osmotic pressure and m is the molar concentration and R is the gas constant in 0.08206 liter atmospheres per Kelvin mole, and T is the Kelvin temperature. Okay. Now note, this is the only colligative property where we use molar concentration and not molal concentration. All right, so if we look at how all our units work out, M is molarity, that's moles per liter. Okay. R is liter atmospheres per Kelvin mole, and your temperature is going to have to be in Kelvin. Well, if you look, the moles will cancel. We got moles on the top and moles on the bottom, and we got liters on the bottom and liters on the top, and Kelvin on the top, or Kelvin on the bottom rather, and Kelvin on the top, and everything cancels except for atmospheres, which is a unit of pressure. Okay, so molarity times the gas constant times the temperature. The temperature has to be in Kelvin. Temperature has to be in Kelvin for this to work. Have to be consistent with your units. So we'll do like we did for freezing point depression. Let's work a problem. So let's say a solution of a carbohydrate is prepared by dissolving 72.4 milligrams in 100 mils of solution, and it has an osmotic pressure of 25 torr at 25 Celsius. What's the molar mass of the compound? So we're going to work this exactly like we did the last problem, where we figured out the molar mass from freezing point depression data. Here we're going to use the osmotic pressure to figure out the number of moles. Okay, so one more time, what are we after? Molar mass. Molar mass is grams over moles. Okay, so we know how many grams we're putting in. So we use the osmotic pressure ultimately to figure out the number of moles from which we can figure out the molar mass then, right? So first of all, we need to convert, we have to do some unit conversions, right? Because I gave you the pressure in torr, and R is the gas constants is in units of atmospheres. Liter atmospheres per Kelvin mole to be specific. So you have to convert torr into atmosphere. Okay, so if you remember from, should have covered this in Chem 1 torr is equal to, or 760 torr rather, is equal to 1 atmosphere. So to convert that into atmospheres, we divide by 760. So that 25 torr is 0.033 atmospheres. Okay. So what we're going to do is we're going to solve for the molarity. Pi is equal to MRT. So we know what the osmotic pressure is, 0.033 M, 0.033 atmospheres. M is what we're solving for. R is the gas constant. Right, and 25 Celsius is 298 atmosphere. And if we solve this, this comes out to be 0.00135 molar. Okay, so remember M is molarity. That's right, that's moles over liters. Moles per liter. Right, so if we take moles per liter and multiply by the liters, that tells us the number of moles. Okay, or rather, I'm sorry, divide by. So 0.00135 moles per liter. I'm sorry, I had it right the first time, multiply. 0.00135 moles per liter times 0.10 liters is 0.000135 moles. Okay. Remember what we're after is a molar mass. A molar mass is grams over moles. So 0.0724 grams divided by 0.000135 moles is 536 grams per mole. Okay, so we got one more thing to talk about here, and that's colligative properties of solutions of electrolytes. So, we didn't really come out and say so. I mean, all the previous examples I used here have been non-dissociating solutes. Okay, things like sucrose. It's a covalent. Sucrose, glucose, they're all covalent compounds. But colligative properties depend upon the number of solute particles. It has, one more time, it has nothing to do with the molar mass of what you're dissolving up. What changes the properties of the solvent is how much solute you're putting in there. How much meaning number of moles. Okay, so if a solute dissociates, the colligative properties are going to be greater than what you might predict. So for example, if you dissolve salt up in water, you should know this from Chem 1, that this salt dissociates into separated sodium ions and chloride ions. So really, the number of particles is twice. Is twice the concentration of the solution. So for example, if you measure the freezing point of a 1 mole sucrose solution, right? Sucrose is non-dissociating. It's a covalent compound, right? It's simply going to be 1.86, right? That's 1.86 times 1, subtract it from 0, because that's the depression, it's minus 1.86 Celsius. And yet, if you have a 1 mole sodium chloride solution, salt, because it dissociates like this, your freezing point is, depression is greater. It comes out to be almost twice. Okay, because, one more time, the amount by which the properties of the solvent change depend upon the number of particles. So, the Van't Hoff factor, which is I, lowercase I, that's the ratio of the observed freezing point to the value that you obtain on the assumption that it acts as a non-electrolyte. Okay? So in other words, hypothetical, what are some hypothetical Van't Hoff factors? Okay, 2 for sodium chloride, right? In the previous example, your salt dissociates into separated sodium plus ions and Cl minus ions, right? It would be 3 for magnesium chloride, right? Because you would get 1 magnesium and 2 chlorides, and it would be 5 for aluminum sulfate, because you would get 2 aluminums and 3 sulfates. Your aluminum sulfate would dissociate into 3 aluminum ions, or 2 aluminum ions, and 3 sulfate ions. Okay. Now, the reality is that you don't quite get what you expect. The actual Van't Hoff factors are a little bit less due to basically some interionic attractions. In other words, there's some ion pairing taking place in solution. And of course, this makes sense that this effect would become greater the more concentrated you make the solution. Okay, so for example, just some numbers. If you had 0.1 molar solution, your theoretical value, what you would expect, would be 3.72, right? That's That's 1.86. That's the freezing point depression constant times 0.1 times 2. Okay, so that's minus 0.372. What you actually get, your actual freezing point, comes out to be like 0.348. So you don't have quite as many free particles as you predicted. Okay, like I said, it's more pronounced for concentrated solutions. So if we drop down to a 0.01 molar solution, what we would predict would be 0.0372 below, or negative 0.0372, and what we get is negative 0.0360, right? So the difference between the two is smaller here than it is here. Okay, and if we drop down to a 0.001 molar solution, then the difference is even less significant, right? So the more concentrated you make the solution, from 0.001 to 0.01 to 0.1, the greater is the discrepancy. And again, that's because you have some interionic attractions. In other words, you have at least some ion pairing taking place. And that wraps up our discussion of solutions and colligative properties.